Okay. What? I just hit the button. Oh, I'll do it at the end. All right, so this one we should know how to do. It's just written a different way, right? All right, so a voltaic cell based on this particular reaction generates a cell voltage of 0.07. So that's typically what you've been calculating, right? But now they're giving you that. And so given the standard reduction potential of nickel in the table, what is the standard reduction potential for this EU that they don't list in the table? All right, so basically, you know, and if we want to do it this way, it was cathode minus anode. Oh, anode. And which one's which? Nickel in the equation is the cathode. Why? Right. The nickel's being reduced, so it's the cathode. And the europium, is that what we decided it was? Is being oxidized, so it's the anode. All right, so did anybody look up the nickel one? Negative 0.26 volts for nickel. All right, so 0.07 volts equals negative 0.26 volts minus X, right? That's what we're trying to find. So X must be 0.33, oh, 35. Whoops. All right, so when we add it, but doesn't that equal negative X? Is it 0.33? I thought, I was like, okay, so it must be closest to which one? And this could be because we're looking on a different table, and this one may be rounded to the hundreds place, where another table may be rounded to the thousandths place, and it may come out a little closer. Because we didn't actually look in table 20.1. We all looked on that sheet I just handed you, right? So, okay. All right, but you get the concept, yes? Easy enough. All right, new stuff. Ready? All right, the other day I said that this kind of is a single displacement reaction, and you wouldn't have to know the activity series anymore. So how does the activity series relate to that standard reduction potentials table? Over here is an activity series, right? Over here is an activity series, and over here is a little half cell thing, right? The little reduction potentials. How are those two things related? Jackson.
Is it like inversely?
Okay,
Like
inverse.
Gold's the least reactive on the activity table, but it's like the most.
Okay, and we don't really, gold doesn't show up on here, but silver does. Silver's up here, right?
It does on my sheet.
And it probably does on your sheet. It's the one I happen to pick. Silver's up here, silver's down here. So they seem to be inversely related. Do the reduction potentials have to be written from positive to negative? No. So be very careful with thinking up and down, and because there have been times that the AP test, yes. Okay, have at it. There have been times that the AP test would give you the reduction potentials in this order, and then the next year they would flip them and lithium would be at the top. So make sure you're looking at positives and negatives. What does the positive voltage tell you? It's easily reduced. So if it's easily reduced, is it an active metal or an inactive metal? Inactive metal, right. Because metals always become what kind of ions? Positive or negative? Positive. Metals become positive ions. So if they're making cations, they are always oxidized. So metals that are very reactive, that are easily oxidized, would have negative potentials, or would be further down on the particular chart I have, right? So lithium would be the most active metal. Okay, so be very careful with up and down and flipping. They are inversely related, and most of the time you see the charts written positive to negative. What about the one I gave you? Is it positive to negative? It's positive at the top. Most of the time you do, but I have seen it the other way. So just make sure you understand totally what it is. So if it's very positive, it's easily reduced. All right, so we don't need an activity series anymore. And when we did single displacement reactions, when we said that they reacted, we meant that they reacted spontaneously. What does spontaneously mean? Okay, it doesn't mean that it happened fast. It just means that it happened without outside help. Okay, they just go. So spontaneity, make sure you know that spontaneous means that it reacts without outside help. Basically, it's going to react. Does it mean it's going to react fast? Not necessarily. Diamonds spontaneously turn into graphite, which is in your pencils, right? But my diamond ring on my hand is not going to turn into a pencil by the time I'm dead, right? Let's hope not. So they just because they're spontaneous does not mean that they happen quickly, okay? That's left for kinetics. That's a whole different study of chemistry. So spontaneous just tells us, yes, it will react on its own. So when you had single displacement reactions, like when you had magnesium plus iron chloride, and you had to decide if the other side would react, what did you go check? The activity series. But what did you really check? The reduction potentials is what you really checked. You just didn't know it because we threw it in the activity series. So you really checked to see if magnesium was more easily oxidized, right, than the iron. And it is. And so they would switch places and you would write the other side. Okay, so the definitive way to tell that a reaction is spontaneous is with this term called Gibbs free energy. And we will do more of this in the thermodynamics unit, okay? I'm going to introduce it because there's some variables. There's a couple of things we're going to introduce today that are going to be taught again later in the year in more in depth, but I'm going to still introduce you to them today. They're not hard, but you're going to see them again. All right, so Gibbs free energy is delta G. Okay, it's delta G, and then when I put the little degree sign at the top, what does that mean? It's standard what? Standard conditions. So that's what the little degree sign, don't forget. And we're going to change from standard conditions today too. All right, so delta G is Gibbs free energy, and how it relates to electrochem is through the equation negative NF E, which is E of the cell. All right, so Gibbs free energy, delta G, is equal to negative NFE. All right, what is N? It's the number of moles of electrons transferred. Okay, when we balance the equation, you know those electrons that you're canceling out, right? You made them equal, so you got 2 or 6 or 10. That's the number for N. So if you crossed out 10 electrons, 10 is what N is. Okay? All right, then F is Faraday's constant. And I round it to 96,500, and that's coulombs per mole. I think your book uses 96,485 maybe. Yeah, 485. Whatever. It's a coulomb. It's a unit of energy. So, well, charge. It's a unit of charge. Okay, and then, huh? That's what I use. You're welcome to be more specific if you'd like, but 96,500 is what I usually remember. So that's what I use. And then E of the cell is the what? The same thing you've been finding. It's the cell voltage. What's some other words for cell voltage? Potential difference, what's another word?
Cell potential.
Cell potential, what's another word?
Electromotive force.
Electromotive force, right. Cell potential. And the EMF, which is electromotive force. I can't fit all that in. All right, so all those things mean the same thing, right? Just whatever particular book or author you're looking at. So we should be able to solve for delta G. We can do it for that equation that we wrote right there, right? Let's do it for this one as an example. So what are we going to have to find E of that cell? Okay, number of moles of the that were transferred. How many moles of electrons were transferred every time this thing reacts? Nah, you're not seeing it because it's a balanced equation. 2, right? Because magnesium goes from an oxidation number of 0 to +2, and iron goes from +2 to 0. Can you see that 2 electrons transferred? Okay, so N is 2. F is down here, it's a constant. How are we going to find E of the cell? Same way you always have, right? The table, exactly. Exactly. So what's which one's the cathode? I never do it this way. So. The cathode is what's reduced. So iron is the cathode. So what's its voltage? No, I heard 3 people. What? 0.77? Is that what iron is? Okay. And then minus whatever the magnesium is. What's the magnesium? Negative 2.3? 3 what?
Wait, no, it's negative 0.45. I was looking at iron 2.
Oh, not to iron 0?
Yeah, it's negative.
Yeah, negative.
Oh, okay. All right, let me change it without erasing half the board here. I always do that. Okay, so this number, we looked at the wrong iron. This number is really what? Negative 0.45 volts. Okay, so negative 0.45 minus a minus 2.37 is going to give us some positive number. What is that? If somebody hit it on the calculator. What?
1.92.
1.92 volts. Can we solve for delta G now? Yeah, because we know everything. So delta G standard is going to be negative 2 times 96,500, and technically that's 2 moles. I should have kept my units. 96,500 coulombs per mole, and then the voltage is 1.92 volts. And there is a conversion. Coulombs is a coulomb is a joule per volt. So can you see that my units, I should have told you that before. Can you see that the unit's going to come out in joules? A coulomb is equal to a joule per volt. What? Well, the moles are going to cancel. You're right. You're going to get a coulomb times a volt. But if you know that a coulomb is a joule per volt, then you get joule per volt, yeah, times volt. And the volts will cancel and you'll be left in joules. Let me do the units. Let me do the units on a separate paper. How about that? All right, here's delta G equals negative NFE. All right, let me just do units. N is in moles. It's moles of electrons, right? Faraday's constant is in coulombs per mole of electrons. And then the E is in volts. I'm telling you, because you don't really know what a coulomb is a joule per volt. That's just what it is. So 1 coulomb is 1 joule per volt. So if I substitute in joules per volt for that coulomb, mole of electron, joule per, now I'm really going to make you look funny, right? But do you still see it all cancel? You should get your answer in joules, yeah. And they could be big numbers. It's okay because most of the time delta G's are reported in kilojoules, so you might get large numbers. That's fine.
So,
What?
I really just multiply those numbers and then just put a joule
And
behind
but you can.
it.
But I'm telling you, the units do work out. That's what I was trying to prove to you, is that the units do work.
I was confused. I was like, so we're gonna have to convert all these numbers over to. Okay.
No. That's what the units come out in, is a joule. Right. So 2 times 96,500 times 1.92, what do we get? Okay. Yeah, see how it's a big number? That's normal. Okay, that's very normal. Because typically delta G's are reported in kilojoules. So we'll just call it 371 kilojoules. Okay, notice the sign on delta G. Is it positive or negative? The sign here is negative. What was it on our E of the cell, our voltage?
Positive.
Positive. Both of those things indicate that the reaction is spontaneous. So when Gibbs free energy is negative, then it is a spontaneous reaction. And when E of the cell, or the voltage of the cell, is positive, it's spontaneous. Okay? And obviously they're inversely related because we have a negative stuck in that equation, right? Okay, so if you're asked to see if it's spontaneous, you can calculate delta G, or you can calculate E. Either way, you're going to get the same result. Okay? All right. Oh, one other relationship. There is a value called K. This is the equilibrium constant. That's a unit. This is a variable. All right, this is an equilibrium constant, and it basically, short and sweet version, it tells you relatively how much products and reactants are left when the reaction comes to equilibrium. Reactions don't all go to completion. Everything you've done so far has, right? Because we do stoichiometry until one hits 0, right? We use up all of one. In reality, that's not what reactions do. They really come to some kind of equilibrium. And this value tells you whether it favors the products, in other words, there's more products than reactants at the end, or if it favors reactants. There's more reactants left in the container than there are products. So the K is the concentration of the products over the concentration of the reactants. Those brackets mean molarity, okay? So the brackets equal molarity. So it's the concentration of the products over the concentration of the reactants. And that's kind of very general, okay? Because it's really raised to the power of their coefficients, and we don't need all that at this point. We just need to know that K is the equilibrium constant, and it's really products over reactants. So if K is greater than 1, does the reaction make more products, or does it make more reactants? It makes more products. So it favors, we say it favors the products. So we have more products at equilibrium than we do reactants. And if K is less than 1, then it favors the reactants. Not real important that you understand the favoring products and reactants at this point. Okay? I'm just going to give you a way to actually calculate the K. All right, so there's a relationship between delta G and K. So delta G equals negative RT ln K. So if... that's delta. I write that?
Delta the triangle?
Yeah, delta's the little triangle. Sorry.
I wrote D last time.
I've been writing D.
Oh, it's a triangle. I've been writing a triangle. It's just my scribble. Sorry. Well, I tried. I meant to write a triangle. I don't know what I wrote. Oh, you thought it was a D? Yeah, it's a triangle. It's a triangle. I will give you. It looked like a D. It's a triangle. It's delta. Delta G. Delta. What does delta mean in math? Change in. Right. The difference. Right. So it's the final minus initial. That's really what it is. All right. Yeah. What? That was my next question. What is that? It is the natural log. All right, so we do have to use logarithms in here.
Wait, I was trying to figure out what your equation is right there. RT what?
RT ln k. All right, ln equals natural log. All right, for now, we do not have to necessarily understand logs or natural logs. You should have all had it at the end of Algebra 2.
No, yeah, we did, but
I know, you got a little video. I know.
There's a
Oh, you didn't even get a video.
we didn't get the video.
I know there's a button on my calculator that says log.
You know what? Honestly, that's all we need right now. There will be times that we'll have to know a little bit more. Yeah, when we get to acids and bases, we'll have to know the logarithms a little better. But for now, as long as you know where the button is on the calculator
We're good.
and the inverse of that, you're fine.
Is it inverse?
Yes.
Yes, there's an inverse function.
It's a second.
All right. What is the difference between natural log and log, though? Do you remember that?
One is organic.
What is organic? What?
One is sold at Whole Foods.
What?
It's natural.
Because it's natural. Thank you. Oh, geez. All right, they're based on, right, in math class, you have log-based gazillions of different numbers down here. Okay, in real life, we have log-based 10 and we have natural log. We don't really use anything else. So log-based 10, if they don't put a number down here and they just write the word log, it's assumed it's log-based 10. It's the log button on your calculator, right? The natural log is on a base of what? E. Good. It's on a base of E. Do you remember what E is?
Yeah, it's like,
At 2.303, 2.03, somebody hit the button. It's 2 something. 2.718 something. 2.718. There we go. All right, so the natural log is just a log. It's the same thing as log. It's just on base E. Okay? 2 different buttons on your calculator. They serve the same function. Logarithms are there to linearize a curve so you can basically extrapolate data off a curve better. That's kind of the point. For you, nothing. Don't worry about it right now. We're not doing graphs. Just don't even worry about it. All we need to know is where the button is on the calculator for now. All right. So if you know delta G, you can now find K. Yes? And if you know K, you can. It's easier if you know K to find delta G, though, isn't it?
Yeah.
Yeah, a whole lot easier. But the other way, we'll probably need to practice. All right, first of all, let me remind you what R is. What's R? Does anybody remember?
It's
gas.
Yeah, universal gas constant.
oh, is it 0.0821?
All right, it's not in this case. You're right, it is 0.08206, but that's liters, atmospheres over Kelvin moles. We need delta G to be in joules, so there's a different value. It's 8.314, and that's joules per Kelvin mole. And since this is energy, right, delta G is free energy, we need it to come out in joules. So we need to use this particular R. I promise you they're the same values. They're just in different units. Okay, and then the other tricky thing is because R is in Kelvin, what does our temperature have to be in? Kelvin. So this has to be in Kelvin.
Are we gonna get something that's in Fahrenheit?
No. Celsius maybe and have to go to Kelvin, but yeah, Celsius to Kelvin, 273, right. All right, so let's find K of the one that we practiced over here. What was our delta G? 371 kilojoules?
Can we just
What? Negative 361 kilojoules. Because I'm going to plug in joules over here, do I probably need to do? Let's just put this back in joules. Let's just make our life simple. We'll put this back in joules. Negative 8.314. Whoops, I forgot my one. Joules per Kelvin mole. All right, what temperature do we want to assume we were working at? Room temperature?
Wait, do we want to do 371,000 or 370,560?
Well, I rounded because I wasn't going to write all those numbers. You may write anything you want on your paper. I'm just showing you the concept. All right, we'll assume we were at room temperature, and so it's 25 degrees Celsius, which is 298 Kelvin, and then ln of k. All right, here's the tricky part. How are we going to solve for k? This is the part you don't know how to, well, you can get part of it. All right, what do we have to do first? All right, so we're going to divide all this mess and we'll get natural log of k by itself, right? So divide all that mess underneath over here, right? So negative 371,000 divided by negative 8.314 divided by 298. I probably ought to do it. Make sure y'all don't mess it up. Huh?
So you have to get the
No,
Wait,
just
how do
divide.
you get the temperature at 298?
I just said we did it at room temperature
Why isn't it 300?
because usually 25 degrees is considered, 25 degrees Celsius is considered room temperature. So it's 298. Did y'all get the same thing I did?
So we just get the
Okay, good. All right, so now that we have 149.7, how do we solve for k?
You get the inverse of natural log.
Right, the inverse. So basically you are raising, right, you're raising both sides. You're putting both sides as the power of e. And I was taught to do this and cross this out, and then k equals, and then so you have to hit e to the x.
It's a big number.
All right, what'd you get?
9.028 times e to the 64.
I get
What?
1.03.
I got that.
Yeah, I got one right.
No. E to the 149.7.
Yeah, 1.03248515.
Wait, what? What did you say?
1.03.
That's okay. That's more what I got. 149 point.
Oh.
And I
This wrong.
no,
You get to 149.
I hit the button wrong. How did I get to the 149?
Yeah, we got a big number.
I just divided. That is what I got.
You signed
1.07 times 10 is 65th.
Number.
Let me do it on your calculator.
Oh, you used the whole number. I didn't use the whole
I
number.
just,
Yeah, that's right. If you use 1. Yeah, I give it 1.03. Right. All right. So we got a really, really, really big K. Yes. All right. First of all, make sure you can get that number on your calculator. You can do it on your cell phones. I promise. If you turn your cell phone sideways, you get the e to the x button.
So this one favors the product.
This one favors the product so much so that there's hardly any, right? No reactants left. So we would say that this one goes to completion, right? I mean, there's got to be minuscule amounts of reactants left to be times 10 to the 65th, right? Okay.
Is that like 65? Is that like in like the quintillion?
Yeah, I have no idea. That was a long time ago. Okay. All right, so here's an example for you to try. All right, so put this one in your notes. Calculate delta G and K for that reaction. Oh, quit whining. You'd think it was Monday or something.
It is Monday.
After a homecoming weekend and a band competition and whatever else you did.
I had an SAT.
Oh, and a SAT.
Oh, but that was fun.
All right, you solve that one. I'll solve it with it frozen, and then we'll see if we get the same answer.
Funny.
You should get the same thing. It's just plug and chug.
Oh, dang.
Oh, wow.
I'll put money on that. I mean, I run a non-profit. I don't have the money.
2. Mm-hmm.
How many ends?
What do you mean?
How many what?
How many not ends? I'm sorry. How many electrons do you have? Because they're both +4. Well, it's all nice and balanced.
Okay, so take it apart into its half reactions and figure it out. Do we need to do it together?
Oh, okay. So I have to take apart in the half reaction. I can just look and tell. It's like on the last one we did. We just looked.
Well, you can if you can think through all of that. Do we need to do it together?
Well, hang on. Wait, no. Actually, I see. Is it? Oh, because if you go by the oxidation number, it goes from 0 to 1, right? And then it goes over here, it goes from 0 to also 0 and
No.
1 to 0. Oh, hang on, I'm sorry. Plus 1 to... Oh, I understand. Okay, so oxygen is reduced and silver is oxidized. Right. So, how many total electrodes? I just count them up, or what? How do you do that? Like, how do you understand the number of electrons? Because I understand that oxygen went to that, and
Right,
silver
but
went
there's
to that.
2 of them. So there's 4 electrons that were transferred. Do we need to do that?
I think I mean,
All right, sounds like we're discussing the electrons a little bit. Let's kind of do this together so we can see if we get it. What I kind of scribbled over here was my thoughts, right at first, was figuring out what was oxidized and what was reduced. So I knew the anode and the cathode. So I figured out that silver was oxidized because it went from 0 to +1, right? And then I was doing E of the cell first. So I went and looked up its voltage, which was 0.8. And then O2 was reduced. It went from 0 to -2. So I went and looked up its cell voltage. And I was getting ready to do E of the cell. So let me go ahead and do that, and then we'll do your number of electrons, because I think that's where your conversations were, right?
Yes.
All right, so 1.23 minus the 0.8 volts gives us what? 0.43 volts for our E of the cell. All right, now, the number of electrons that transferred, it's not 1. Because you really have, it is 1 in that half reaction, right? But in this one, and you can look at it right off your reduction potentials table if you want. They're written there. If you look at the O2 plus 4H plus 4, right? Yields 2H2O. What did we have to multiply this one by to get that balanced equation? So what number of electrons did we end up canceling out? So N is 4. N is 4. Do you see how the 4 came about? All right, this is one half reaction, yes? This is the other half reaction. Where did I get all that mess? Right, I just looked straight off the standard reduction potential table because it's written there for me, right? You could have balanced it and solved it, right? I mean, you could have added different numbers of stuff, right? So you would have added 4H plus, and then, you would have added 4 electrons. You could have balanced it yourself, or you can look right off the electron potentials table. But then when you go to put them back together in your balancing, the electrons have to be equal. So we would have to multiply this one by 4, right? And then when we went to add those back together, the 4 electrons would cancel. So 4 is the number of electrons. That's N. Okay, are we okay there on finding the electrons? All right, so we have E of the cell, we have N, and we know F because F is the constant, right? 96,500. Oh. So now you should be able to do it. I'm going to erase this mess down here. Joules or kilojoules is fine. You can leave them in joules because you're probably going to need it in joules for the next one.
I don't like spelling check. It's bad.
But it's gonna be like run it.
You gotta go do
If we keep all the significance, is that what you got for delta G?
It's negative actually.
Oh,
Yeah.
negative. I dropped my negative. Thank you.
Wow, Robinson.
I know, I'm terrible. Okay, so there's delta G. And now you got to find K. So delta G equals negative RT ln K.
Is R 8.314 or
Yes.
0.814?
No, 8 point.
8 point.
8.314.
You still have
I'm going to drop my unit so it'll fit. What temperature? 298.
I do. It's just that. You know.
Yes, sir.
Wait, is that the answer?
No. Yes. I mean yes. That's the answer. Yes.
I don't trust you.
Trust with your friends. Oh yeah.
I'm about to get
What?
Do you need to round?
You can round, or you can carry all your numbers down.
I mean, even the slightest thing can change, especially doing a big power.
Yeah, but that's one reason you're showing all your math. I'll be able to see your rounding.
It did turn out this time.
Right.
You get 1.24 E29.
Yes.
I got it.
Okay, is everybody able to get the K on the calculator?
Yes. Do you care if we write E29?
I really do care if you write E29. I hate the E29.
I love E29.
I'm not saying it doesn't work, but you need to show me that you know that E stands for times 10 to the something. It's not wrong. It's just I don't like it. Yeah. Because to me, it seems like you're just copying something off your calculator and you don't really know what it means.
I don't know what it's
But what do you know? I know what it means.
Well, then I have to trust that everybody knows, and I
I
don't.
mean, Kevin probably knows.
He just threw you under the bus quick, Kevin.
That's fine.
Will, poor Will.
That's
Done.
fine because I get fit under the bus and I'm fine. I'll be fine.
All right, we're comfortable with delta G and K. They're just calculations, yes? All right, and you notice that really big Ks, negative Gs, and positive E's happen to be spontaneous reactions usually, right? Okay. All right. You won't ever get a negative K. You'll just get less than 1. It won't ever be negative because it's a ratio of things that are always positive because they're concentrations. So good question. All right, what happens? What happens if we are not at standard conditions?
Everything goes wrong.
I've got like 15 minutes to teach the rest of this, and this is the hard math. All right, that was the easy path.
That wasn't that bad.
No, it doesn't. It's not much harder. It's safe. All right, refresh your memory. All right, the good news is your mastering chem for this is not due until Friday, and the quiz. What are? The good news is that your mastering chem for this is not due until Friday, and your quiz on this is not till Friday. So you have a lab on Wednesday. So before you leave, make sure I give you your lab so you do your pre-lab. Or did I copy?
What?
Oh no, I think I forgot to copy your lab.
Yeah.
Oh, it'll be on Canvas, not a problem.
Still gonna forget to do it.
Answer the pre-lab. You need to have a pre-lab done before you come, and you need to read it. So,
So we have to
yeah, you can do it on a separate piece of paper. Or you can print it out and write on it if
I
you'd
don't
like.
have any paper.
Or you can come back to me tomorrow morning and I'll have it copied.
I don't know.
Can you just print it out tomorrow?
I can. You're welcome to come by and pick it up.
No.
All right, remind yourself. Let me teach or you're going to be lost.
I
All right, remember what standard conditions are. What are they? Room temperature, which is 25 degrees C
One mole.
or 298 K.
760 torr.
1 atmosphere, or if you'd like, 760 torr.
Or millimeters mercury.
Or millimeters of mercury. Somebody go turn the TV off. All right, and then what's the solution concentration?
1 molar.
1 molar. Okay, what they typically change is the concentrations. Okay, so this, yeah.
Go through this, Eli. Sit down. Alright.
Eli sits on the other side of the room. He doesn't know this.
Eli's really confused.
Yeah.
Eli,
Okay. Shh. Focus, focus, focus. All right, we've got 1 molar copper 2 sulfate, 1 molar zinc sulfate. We'll say we're at 298, and we don't really have any gases, so we don't care that we're at 1 atm. All right, so this would be a standard cell, right? You know how to find the cell voltage of a standard cell because you go look it up. It's zinc and copper, and we cathode minus anode, and we can find that value, yes? What happens, though, when this is not at 1 molar? Let's say it's at 0.5 molar. I don't know. What happens? I'm sure you can make the other one 0.5. Is it at standard conditions? No. All right. So once something changes, let's just leave one of them at 0.5 for right now. Once something changes, it's going to affect your voltage. And the equation, and they do a nice little derivation, but I can't derive it for you because you don't know the delta G real equation yet. So you're going to have to just trust me. That E of the cell at non-standard conditions, so I'm not putting the little degree sign up here, is equal to E of the cell at standard conditions minus this correction factor, RT over NF ln Q. What? Exactly. All right, we know how to find that, correct? We know what R is because it's the 8.314 again. We know what T is. It's temperature in Kelvin. We know what N is because it's what?
Number of electrons transferred.
Number of moles of electrons transferred. And what's the F?
96.5 K.
Right, it's Faraday's constant. We know that that's natural log. So now we have this Q problem, right? What is Q? No. Q is basically the same thing as K, except it's not at the end of the reaction. It's at the beginning of the reaction. So it's still products over reactants. And they're raised to the power of their coefficient.
What?
Yep. All right, this one probably balances and doesn't have coefficients. So, because we have zinc plus copper 2 plus goes to zinc 2 plus Cu. So in this case, they're all 1 to 1 to 1, right? So the only thing that's going to change, this Q for this reaction is going to be 0.5. No. Why did I write that wrong?
Because you put the molar.
Well, yeah, that's what brackets mean. Brackets mean molarity. But what did I do wrong? Where is the copper? Right. The 0.5 is the reactant, right? Because the copper 2 plus is a reactant. The zinc 2 plus is a product. And these are the only things, these aqueous things, are the only things we're worried about in here. Solids don't have a concentration. They're pure whatever they are, right? So they don't really have a molarity. Or you can say the molarity is 1 or something. They're pure. So that's what I did wrong. This is a reactant, not a product. So I should have 1 molar on top and 0.5 molar on the bottom. So it's 2. So Q is 2. All right, so how does that affect the voltage of the cell? All right, we're going to have to find the standard cell voltage. So somebody look on your little sheet and tell me the zinc and the copper's voltage. What's the zinc's? Negative 0.76. And what's the copper's? 0.34. Like that? All right. No? Did I write it backwards? Negative 1 point what? Oh, 1. Do I have these two backwards? Is that my problem? Which one's the cathode?
It says it right down there.
Yeah. So this was the zinc and this was the copper, right? So I wrote it backwards. This is why I never do it this way. All right, so it should have been 0.34 minus a minus 0.76, right?
Negative 1.1.
So it comes out 1.1.
Yeah.
All right, so we should get 1.1. All right, so now we need to know if this is going to go up or go down. Punch in your calculator the natural log of 2 and tell me if it's a positive or negative number.
Positive.
What makes the natural log of Q go negative?
The negative natural log.
You're never going to have a negative Q.
It's like a smaller decimal.
All right, so less than 1. When Q is less than 1, right? Punch in your calculator like 0.2 or 0.01 or something.
Or what? Natural log?
And then hit natural log.
Because the negative 1 will be the inverse of.
Right. So, okay. So when Q is bigger than 1, what does it do to the cell voltage? It goes down because we're going to end up, all these numbers in here are positive, yes?
Right, so the bigger the Q, the smaller the voltage.
Mm-hmm. The more it's going to reduce the standard voltage, yeah. Okay, so now you can plug and chug, right? You can do that part. So E of the cell equals 1.1 volts minus, and then it's going to be 8.314, 298. How many moles of electrons transferred?
1.
No,
So
2. And then 96,500, then natural log of 2. So punch all that in your calculator, and somebody tell me what my new cell voltage is. Yeah, magic. Yes.
What did you say? A minute ago? Plug and chug?
Mm-hmm.
I got 0.75.
0.75.
What's the chug?
Did anybody agree with him? No? Not what you got? 1.09? Oops. All right, can anybody, somebody else got 1.09? Anybody else get that?
Wait, do that last.
Oh.
Yeah, that's right.
Oh,
1.09? All right, so a couple of people got that, so that must be right. All right.
Order operations.
Order of operations matters. There we go. All right, so do you see how to calculate it at non-standard conditions? All right, because concentration can be a driving force, you can actually have a cell that is considered a concentration cell. And you can have the same thing on both sides. So in this case, see how there's nickel and a nickel solution, and I get a voltage. But it's because they have two different concentrations. When those two concentrations become the same for the same element, you get no voltage. So eventually it will go to 0, but initially, while the concentrations are different, you will get a voltage. So it works the same way. It's the same equation. It just looks funny to you because it's nickel on both sides. You're like, how in the world? So your equation is nickel, right? Goes to, it looks like that, which looks funny to you. Yes? It's a little easier to see it. Like if I make this one red, where is that one? If this is the cathode and this is the anode, where is this one in that equation? Is it the reactant or the product? It's the reactant. So this is the red nickel 2+. That will help you if you will do that. That will help you when you go to find your Q, right? Because your Q ends up being nickel 2+ over nickel 2+. Well, which one's which, right? So this one is the one we circled in red, right? All right, so you can still do E of the cell equals E of the cell standard. What is E of the cell standard? Off the top of your head, you should know, right? What is it if it's standard? If they're both 1, it's 0. Right, this is 0 in a concentration cell.
The whole thing's 0.
E of the cell is 0. You still have this part. So the concentration gradient drives the voltage, drives the cell. Okay? And you can plug in all of that. How many electrons transfer? 2. And what would Q be for this reaction? For this particular over here? Q would be 1 times 10 to the negative third over 1, right? So it's 1 times 10 to the negative third. So if you took the natural log of that, is that going to be a positive or negative number? Negative. So if it's negative times a negative, you're going to get a positive voltage, right? So it's spontaneous, right? So the fact that it goes from a lower concentration, the electrons will run from the lower concentration to the higher concentration. Which makes sense, right? Because it's going to lower that higher concentration. As soon as you put electrons into this solution, what starts coming out? The nickel, right? Because it turns into nickel atoms, which means the concentration of the nickel 2 plus is getting smaller and smaller and smaller, right? Until the two become equal. And then when they become equal, it'll stop. The reaction will stop. Okay, does that help? A little bit? All right, there was an example, but I don't know that we have time.
Probably not.
I don't know that we have time for an example. We did it with the other one. It literally is just plug it into those equations, but they take a little bit of time. All right, the Master in Chem said it took about 53 minutes to do, but you have until Friday. I'll put the lab on Canvas, but if you want to come by and pick it up, you can do that pre-lab and read the lab before Wednesday.
Because we went through this way
Quiz
faster.
on Friday.
We went through this way faster than